Yes. Hello everyone. So we are discussing question based on center of mass reference frame. Like some questions becomes very easy when you solve it with the center of mass reference frame. So one such question for an idea for the students to get an idea like how to how would it be helpful if you solve a question with center of mass reference frame, right? Let's try this. It says that there are two beads having masses 6m and 12m. They're connected with a light spring. Okay. The beads can slide over a frictionless parallel horizontal rail as shown in the figure. The lighter bead is given an initial velocity of v naught in the horizontal direction. Calculate the maximum extension produced in the spring. So, in the question, they have given a diagram. Let me draw that diagram first. As per the question, we are having two rails, horizontal rails like this, and on the rail we are having a 6m mass and a 12m mass. So this is the 12m and this is the 6m, and connecting them is a spring like this, and a velocity of v naught is given to the smaller mass, the 6m mass initially. Lighter bead is given an initial velocity v naught in the horizontal direction. Calculate the maximum extension produced in the spring. Okay. So because of this velocity that is given, don't you think that after some time, this bead will be moving along this path and may have reached somewhere here? And because of the motion of this bead, the spring might also get extended a little bit, and because of the extension in the spring with spring constant k, because of the extension in the spring, the mass here would be also experiencing a force. Because of that, this mass also starts moving. So after some time, let us say my masses are at this location with the spring in this way. So the spring has already extended a little bit. At this moment, the velocity of this, let us say, as v1 in this direction, and this one has a velocity v2 in this direction. And if I say this angle is theta, then because of the parallel rays, we can say this angle will be also theta. Along the line, if I draw like this, then this angle would also become theta. Why I am doing that? Because this is v2. Can I consider a velocity component in this direction as v2 cos theta, and same way a velocity component in this direction v1 cos theta? My point is, until when will the spring keep extending? The spring will keep extending until when the v1 cos theta becomes equal to v2 cos theta. Basically, the velocity of approach or the velocity of the recede should become zero. That is the relative velocity along that line. When it becomes zero, that's when the spring will achieve its maximum length, or it will achieve a constant length at the end. That's the point. And that will be the maximum extension. So that basically I am interested in getting this relationship, that is finally when v1 is equal to v2, let us call it as a common v, when this happens, that is when I am having the maximum extension in my spring. Okay, all the students should be able to imagine this scenario, that when will the spring achieve the maximum length. Okay, because both the 6m and the 12m, when they are having a relative velocity along the line of their action, the spring's length will be continuously varying. It can either increase or it can decrease based on the relative velocity. But if the relative velocity itself is becoming zero, that means no more relative motion. So the spring's length has become constant. And in our case, that final length would be the maximum length of the spring. So based on that understanding, once we got this, we can now use or take the help of, let us say, conservation of momentum. Along horizontal direction, we can say there is no friction force, there is no other force acting. So we can say along horizontal, I am using conservation of momentum. Please remember, this is not center of mass. Conservation of momentum I am using. So initial momentum only 6m was having. So 6m into v naught, correct? And finally, both of them are having some velocity. So I can say it as 6m into v plus 12m into v. They both are having same velocity at that moment. So if that is the case, I can say 6m plus 12m times v. So from here I can get the V is equals to 6m divided by 18m v naught and this comes out to be v naught by 3 is my final velocity. So I got the final velocity that the system would be achieving. That means both of them would be achieving. Now at the end, I am interested in the spring extension. This can be easily found out because again there is no friction, no dissipative force. I can say conservation of mechanical energy is valid. According to conservation of mechanical energy, initial kinetic plus potential energy should be equal to final kinetic plus potential. Initial kinetic is half into 6m into v naught square. This 12m had no velocity at that time. Plus the spring was in its natural position, that is natural length, no extension. So no potential energy in the spring. And finally, half into 6m is having a velocity of v square plus half into 12m is also having a velocity v square, and also the spring would be having some half k x square. So all these energies are there at the end. That x is the total extension which we need to find out. So from here, first of all, we can remove all the halves. Okay, and this is basically 6m v naught square equal to 6m v square plus 12m v square is 18m v square, which is nothing but v naught by 3. So I can write it as v naught square by 9, which will give me 2 times m, which can come here and become 4 times m v naught square equal to half is not there, it's gone, kx square. That's it. So from here I am going to get the value of x is equal to I'll be having it as a 2v naught under root of m by k. Okay, so this is the maximum extension that I'll be getting finally. This x that I have obtained is also the x max. So what all steps we used? We first of all identified that finally the velocities would be equal, that we had to do. Then we had to conserve the momentum of the system, and then we have to also do the conservation of mechanical energy of the system. So all these steps we did. Now we can also solve this question without going about in this way, but by solving it from the center of mass's reference frame. From center of mass reference frame. So from the center of mass reference frame, we can write down the work energy theorem. Let's write, right? Work energy theorem, if I write, I can say the net work done should be equals to change in kinetic energy. And in a modified form, the same thing I can write it as net work done can be because of two forces. One is work done by the external force plus work done by the internal force, that is equals to change in kinetic energy. Remember, I am considering this equation with the center of mass as the reference frame. Okay, so that you have to be careful. Now, with when I talk about external work done, there is no external force acting. There might be some normal force from the railing acting on the body, but we are considering that work done to be zero, because you understand normal force would be normal to the railing and displacement is happening perpendicular to that. So work done by any external force, gravity is not there, we are not considering that. So all the work done because of external is zero. Work done by internal. So internal force between the system, between the two bodies, is nothing but the spring force. And spring force work done is a conservative one, right? Because it's a conservative force, the spring. That's why the same work done can be also written as minus of delta U, which is nothing but change in potential energy. All of you might be knowing that work done by a conservative force is also equal to the negative of its change in potential energy, and that's equal to change in kinetic energy. Now this, when we write, we have to be careful, because kinetic energy, because of with the center of mass reference frame, can be always written as half into mu into Vr square. Now what is a mu here? This is what you should be learning. Mu is called as reduced mass. Reduced mass. And Vr is basically the relative velocity. Relative velocity. So we can use that right now here. What relative velocity? First of all, relative velocity between the two bodies. Okay, let's apply that. Let's see. So kinetic energy change can be written as a final kinetic energy minus initial kinetic energy, right? So let us talk now. This one would be half kx square, the final extension that it has had, equal to final kinetic energy. When I write, I should be writing it as half into mu into final relative velocity. Now at the end, both of them should be having same velocity we discussed. If they are having same velocity, what's the relative velocity? Finally, it will be 0. Okay. What about initial kinetic energy? So initially, we will be writing the same way, half mu. Now, what's the relative velocity initially? This body that is 12 m mass is stationary. Other one is moving with some velocity. So relative velocity would be just that v naught itself. So directly we can write it as v naught square. That's it. So now if you solve it, you'll be getting this would become 0 basically. Minus minus gone, half gone. Basically, you'll get kx square is equals to mu. Mu is nothing but reduced mass. What's the formula for the reduced mass? Those of you don't know, mu is always written as m1 m2 divided by m1 plus m2. This is the formula. So I can write it as 6m into 12m divided by 6m plus 12m times v naught square. So this will become 18,634. So I'll be getting a 4m in that location. 4m v naught square is equals to kx square. If you just compare this thing with this, I think you understand we are getting the same answer. That is x is equals to 2v naught root of m by k. And this also gives me the maximum extension because we are considering finally the relative velocity to be 0 for the two bodies. I hope you have understood. This kind of questions are very interesting with the center of mass reference frame because majority of the students don't feel like or they don't wish to study this center of mass reference frame. They feel like it's too complicated, but it's not really. In fact, it makes your calculation pretty easy, right? I had done all these steps because I wanted to show that how the steps are being done. But if I am a student and doing this in the examination, I can skip many of the steps. I don't need to write this step. I don't need to show that its external is 0. I know that final kinetic energy is 0. I know that. So basically, after writing this equation, I can directly jump into this equation and I can write it. So basically, in what 4 or 5 steps, my answer would come. Whereas here, I have to do all these steps and then I'm able to get the answer. Okay, so this question, the difference doesn't seem big, but in many questions and some other questions actually, we find that conservation of momentum and conservation of energy method may go a little bit lengthy compared to solving it with center of mass reference frame. That's why this kind of method is important. So make sure that you understand it and ask any questions that you have in the comment section. Okay, we'll be stopping here. A very important question. Thank you.